All right, hey, organic chemistry. I just wanted to walk us through the notes that we've taken in class just in case you missed it or you need somebody to re-explain it to you. So in these first pack of notes, it's very important for you to remember how to draw Lewis structures, recognize functional groups, and then in these notes, I talk about what percent composition is and how we could calculate it, and eventually get formulas and predict shapes and structures of molecules. So just to remind you, and we've had these notes before, the group number on a periodic table, which is up and down, is equal to the number of valence electrons. Those are the electrons in the outermost shell. And so remember that if I have an element, let's say it's carbon, and it's in group 4, it has 4 valence electrons. And then eventually we could use this information about valence electrons to construct what's known as Lewis structures. If I count all of the valence electrons, which are the electrons that are used for bonding, they could combine in a specific way to form these structures. And then don't forget that a line represents 2 electrons that are in a bond, and these 2 dots here represent a lone pair, and 1 dot is an electron. And now all atoms combine in order to form what's known as an octet. Now some elements can have over an octet, and those are elements in period 3 and higher. So this is period 3 and higher. These elements can have over an octet. So that's like chlorine. Chlorine can have over an octet. Okay? Moving on, there were steps. Now, for our class, you don't have to memorize these steps. You just follow the steps in order. But there were steps in order to use these valence electrons to construct Lewis structures. So we did NH3. Well, reading it up here from the total atom altogether, nitrogen is in group 5, so it has 5 valence electrons. Each of the hydrogens has 1 since they're in group 1 times 3, total of 8. Next step, add or attach the atoms in the compound to each with a single bond over here. And then, so that was nitrogen and 3 hydrogens. Now, since there's only 1 nitrogen and 3 hydrogen, nitrogen's probably going to be the central atom. That's the common sense way of looking at structures. Or typically the element on the left will be the center atom, so I put nitrogen, I attach them all with a single bond to hydrogen. Now each bond, that's before I put the dots on, each bond is 2 electrons, 2 times 3 is 6, from the 8 that we had before. Left over goes on the central atom, or I have to make sure that everybody has an octet before I put that on the central atom. Now a hydrogen is one of those cases that hydrogen only needs 2 electrons or 1 bond. Boron doesn't require an octet. And elements S, Cl, Bri, things that are in period 3 and higher can have over an octet. So this hydrogen has 1 bond, that's good. This nitrogen, before it has this lone pair, 2, 4, 6, it needs 2 more, and those are the 2 that was left over, boom. On our first day, I made you draw CS2. So CS2 got us all the way down here. If there are any remaining electrons left over, you put them on the central atom. If there are none, if there are not enough electrons available to give each atom an octet, multiple bonds may be formed. Typically, carbon and oxygen and nitrogen may have double bonds. Carbon and oxygen can form double. Nitrogen typically forms triple. And so that happened when you did this CS2. First you drew this. There were no electrons left over, and so you had to make double bonds or multiple bonds between carbon and sulfur. And then to remind you, if a compound is an ion, which means it has a charge, you add electrons to the total for each negative charge, and you subtract electrons from the total for each positive charge. And then continuing on, make sure you get this if you follow the steps for the next example. Make sure you get PF3 with a lone pair on the central atom, following all the steps. And then make sure you could do SCl4 with 1 lone pair, and all those chlorines have lone pairs, 3 pairs of them. Following the steps, you should be able to do SCl4. And then finally, make sure you could do boron, BF3. And a lot of people were doing this with boron. Boron doesn't need an octet. Boron's one of those special cases that doesn't require an octet. Typically, it forms 3 bonds. So typically, we'll have boron with 3 bonds, and we're good to go. All right, on the next page, and you might want to pause and highlight and get all this information, but all of this stuff was from last semester, and we went over functional groups. So make sure you read and highlight and see where I could identify a functional group. Alkanes are all single bonds, they end in ane. Alkene has a double bond, they end in ene. Alkyne, triple bond, end in ine. Arenes are this alternating double and single bonds in a ring, ends in ene. Okay, alkyl halide, aryl halide. I'm highlighting the different parts of the functional group. Then we have alcohol, phenol, ether, aldehyde, ketone, and carboxylic acid. Alcohol is the OH. Ether has an oxygen bridge, ROR, where R is any carbon-containing compound. And then aldehyde, ketone, and carboxylic acids all have the C double bond O, but an aldehyde has a C double bond OH. A ketone has a C double bond O with 2 carbon groups connected to it. And carboxylic acid has C double bond O with OH. And then ester is C double bond O with carbon groups. Amide has C double bond O with a nitrogen next to it, and amine is just a nitrogen on a carbon. And then we went through and did some examples and identified some functional groups again, so you could pause and copy this. Alcohols are OH, and so I circled them in the compounds. Over there. Carbonyl comes for those ketones, aldehydes, carboxylic acid, ester functional groups. Carbonyl is a C double bond O. We will see that a lot this semester, and I circled them in compounds. Sulfhydryl is not really big in what we're doing this semester, but just wanted to recognize and identify them. Amine, again, we have nitrogen. Aldehyde is C double bond O with an H. Ketone is C double bond O with carbon groups on either side. And again, R is any alkane or alkyl group. So you might want to pause this and copy and circle and make sure that you could identify those functional groups. And then to make sure you understand this, make sure you do this practice. So if you watch this video, you did this practice and recognizing functional groups. I'll do a couple. I did number 2. This is a nitrate. And number 16, this is a new one. This is a nitrile, a C triple bond N. But let's say I was looking at something like this one. R, C double bond O, O, R. Well, C double bond O, O, if I look back 2 pages, if I have a carbonyl, which is a C double bond O, and then there's another oxygen, that's ester. C double bond O, O, R, that's ester. So that's how I want you to do these examples and show me them if you did not show me them already. And then something like this one, C double bond O, and then a nitrogen. This is an amide. This one is C double bond O with a hydrogen. This is an aldehyde. I'll do one more. How about ROR, which could be something like alkyl group and then oxygen. This is an ether. All right, so make sure you do the rest of these to make sure you can identify functional groups and compounds. And then we went over and started beginning something known as index of hydrogen deficiency or elements of unsaturation. These are 3 different things that are an element of unsaturation. Either I could have a double bond, I could have a triple bond, which actually has 2 elements of unsaturation, 2 elements of unsaturation, or a ring. If I see any of these in a structure, it's an element of unsaturation. So if I see this compound, this has 1 element of unsaturation, it has a ring. If I see a compound like this, there are 2 double bonds. Each double bond is 1 element of unsaturation. There's 2 altogether. This has 2 elements of unsaturation. This has 1 element of unsaturation. We call that EU. Now, in order to calculate or identify that, we have to know this formula, CnH2n plus 2. This is the formula for a completely saturated, which means it has all the maximum hydrogens that are attached to a carbon. So this top box is a saturated table. These have carbons that have all the possible hydrogens. So for example, if I had 8 carbons, if N was 8, H should be 2N plus 2, which is 2 times 8 plus 2, which is 18 hydrogens. I should have that in total. You need to know how to calculate the hydrogens required for a saturated hydrocarbon, because we're going to compare that to other things like alkenes, which are a 2N rule, or an alkyne, which is a 2N minus 2 rule. And I talked about we have this issue because both of these have the same exact molecular formula, C6H10, but how do I know something has 1 triple bond or something has 2 double bonds? These both have the same exact formula, and I put it under the alkynes table, so I know I had to draw that. But in the future, how am I going to know if something has 1 triple bond or 2 double bonds? And that's why we talk about elements of unsaturation. Okay? So, index of hydrogen deficiency, elements of unsaturation. I had this big structure here. And like I mentioned before, there are 3 different things that we could recognize as an element of an unsaturation. A ring, a double bond, or a triple bond. So, in this compound, I have 4 rings and 1 double bond. So 1, 2, 3, 4, there are 5 elements of unsaturation just by looking at it. 4 rings and 1 double bond. Now I can calculate these elements of unsaturation by using the CnH2n plus 2 rule. I gave you the molecular formula in class as C27H46O4. And we could follow these steps to calculate getting 5 elements of unsaturation. The maximum number of hydrogens is supposed to be 2n plus 2. You count halogens as hydrogens. So when I say halogens, X is F, Cl, Br, or I. So if I see those, I count them as hydrogens in my formula. You ignore oxygen, and for nitrogen, you subtract 1 hydrogen for each nitrogen and ignore nitrogen. And so let me do the example that I did in class. We had this structure is C27H46O4. Now, to get the maximum number of hydrogens, it's supposed to be CnH2n plus 2, where N is the number of carbons. So I plug that in. 2 times 27 plus 2, I'm supposed to have 56 hydrogens, but I only have 46 hydrogens. Now, 56 is the maximum number of hydrogens I should have, but I have 46. That means I'm missing 10 hydrogens. Now, to account these as an element of unsaturation is the number of pairs of hydrogen atoms that we would have to add to the molecular formula to get the corresponding saturated carbon. And so the question we ask is, how many H2s did I lose? Again, how many H2s did I lose? So if I get my total number of hydrogens that I lost and I divide it by 2, that's my number of elements of unsaturation. So in this problem, I have 46 hydrogens, but I'm supposed to have 56. 56 minus 46 is 10 hydrogens. Dividing by 2, I have 5 H2s that I lost, or 5 EUs. And those are the 5 EUs that I calculated or I showed before. 1, 2, 3, 4, 5. We predicted 5 elements of unsaturation, and we also could show how we could calculate it. I'm going to do a couple of examples to make sure that you got this idea. So let's do just 2 of them. Just by looking at this structure, how many IHDs or elements of unsaturation? IHD is index of hydrogen deficiency, but I like to use EU as elements of unsaturation. Just by looking, there's 1 ring. So that's 1 EU. The molecular formula of this is C6H12. There are 6 carbons, 1, 2, 3, 4, 5, 6. And then each of those carbons, since they're all in a ring, have 2 hydrogens. So that's 12 hydrogens. To calculate, I need to do CnH2n plus 2, where N is the number of carbons. To calculate, N is 6, so I should have C6H2n plus 2. 2 times 6 plus 2 is 14. I'm supposed to have 14, but I have 12. Minus C6H12, that's 2 hydrogens. If I divide by 2, that's 1 EU. For how many pairs of hydrogens did I lose? 1 pair of hydrogen, or 1 element of unsaturation, which is what we predicted. Let me do the last one. Just by looking at this structure, I have 1 ring and 1, 2, 3 double bonds. 1 ring, 3 double bonds. Altogether, I should have 4 elements of unsaturation. Just by looking at this structure, there is 1, 2, 3, 4, 5, 6 carbons, and 1, 2, 3, 4, 5, 6 hydrogens. I kind of already helped by drawing them in, but each of those carbons show 3 bonds, and they're supposed to have 4, so that 4th one is a hydrogen. Now, if I want to calculate it, I could do it like I did before. For something with 6 carbons, there's supposed to be 14 hydrogens. So C6H14, because of the 2n plus 2 rule, for saturated, I'm supposed to have 14 hydrogens, but I have 6. Oops, C6H6. If I subtract, I have 8 hydrogens that are missing. If I divide by 2, I have 4 H2s that are lost, or we call that 4 EUs. And guess what? That was the prediction of 4 EUs being missing. Okay, I'm going to end this video here. This is something that's a bit new. I'm going to end with you being able to do elements of unsaturation. So make sure you could do the rest of this practice if you hadn't already. So you could look at a structure and count and calculate elements of unsaturation. In my next video, I'll talk about percent composition and proposing structures altogether.